What if you could make AI models smarter, faster, and fairer, all at the same time? That's the question we're tackling today. We're diving deep into some cutting-edge research that's pushing the boundaries of what's possible with large language models.
Exactly. We've got a packed agenda, so let's jump right in. First, we'll explore a surprisingly simple trick to boost a model's reasoning skills using minimal resources. Think of it as giving your AI a targeted study session right before the exam.
Then we're unraveling a new way to understand and use electronic health records. We'll break down how a special type of AI called a transformer can learn from all that complex medical data to predict things like hospital stays and even Alzheimer's progression. We'll explain what a transformer is in plain English. Don't worry.
Next up, we're tackling efficiency. We'll look at a clever technique to fine-tune those massive language models without breaking the bank or your computer. It's all about finding the most important parts to tweak, kind of like focusing on the key ingredients in a recipe.
And speaking of efficiency, we'll also be discussing a new way to compress these models, making them smaller and faster without losing their smarts. Imagine shrinking a giant textbook down to a pocket guide without missing any crucial information.
Finally, we're turning our attention to fairness. We'll introduce a framework for measuring bias in AI, but with a twist. It focuses on local cultures and contexts. Think of it as making sure AI understands and respects different communities, not just one.
So buckle up, because we're about to unpack all of this. Let's get started. All right, let's dive into this paper on test time scaling for language models. The core idea here is pretty straightforward. Can we make language models perform better by giving them more computational resources during the testing phase, not just during training?
Exactly. It's like saying, okay, you've learned all this stuff, but now let's give you some extra time to really think through the problem before answering. The paper highlights how OpenAI's O1 model showed this capability, but they didn't share the details, which sparked a lot of attempts to replicate it.
And that's where this paper comes in. They're trying to find the simplest way to achieve test time scaling and strong reasoning. Their approach revolves around two key things: a curated dataset called S1K and a technique they call budget forcing.
Let's break those down. First, S1K is a dataset of just 1,000 questions, but they're carefully chosen to be difficult, diverse, and high quality. They actually validated these criteria through ablations, which is a fancy way of saying they tested how important each criterion was.
Right? They started with a much larger pool of questions, around 59,000, and then filtered it down to this focused set of 1,000. They looked at things like question quality, making sure the formatting was good and there weren't any weird errors. They also made sure the questions were challenging enough that the models couldn't just breeze through them.
And diversity is key too. They wanted questions from different fields to cover a range of reasoning tasks. They even used the mathematics subject classification system to categorize the questions, ensuring they spanned areas like geometry, number theory, and even some physics and economics.
Okay, so that's the data. Now, what's this budget forcing all about?
Budget forcing is a clever way to control how much compute the model uses at test time. Basically, they can either cut the model's thinking process short or extend it. If the model is rambling on too much, they forcefully end the thought process. Or, if they want the model to explore further, they add weight to the model's generation to encourage more exploration.
So it's like giving the model a nudge in the right direction. Hey, you're done. Give me an answer. Or hold on. Keep thinking. You're not quite there yet.
Exactly. And the cool thing is, this simple technique, combined with fine-tuning a language model, Quen-tuned 532B instruct, on their S1K dataset, allowed their model S132B to outperform OpenAI's O1 preview on math competition questions.
That's impressive. They're beating a closed-source model with a relatively small dataset and a straightforward technique. It really speaks to the power of careful data curation and smart test time interventions.
And it gets better. They found that scaling S132B with budget forcing allowed it to extrapolate beyond its initial performance. It's like the model learned to use the extra compute to its advantage, leading to even better results.
So, to recap, they've shown that you don't necessarily need massive datasets or complex reinforcement learning to achieve test time scaling. A well-crafted dataset and a simple technique like budget forcing can go a long way.
Definitely. And the fact that they've open-sourced their model, data, and code is a huge win for the research community. It allows others to build on their work and explore this area further.
They also did some interesting ablation experiments, right? Like testing the importance of those difficulty, diversity, and quality measures in their dataset.
Yep. They found that if they just randomly selected questions or only focused on diversity or difficulty, the performance dropped significantly. It really highlights the importance of that careful data selection process.
And what about the different test time scaling methods? How did budget forcing stack up against the alternatives?
They compared budget forcing to things like conditional length control, where you tell the model in the prompt how long to generate for, and rejection sampling, where you keep sampling until you get a generation that fits a certain length. Budget forcing came out on top, offering the best control and scaling behavior.
So it's not just about getting the best accuracy, it's also about being able to predictably control how the model uses its compute budget. That's a really important point.
Exactly. They even defined a set of desiderata for evaluating test time scaling methods, focusing on controllability, scaling slope, and overall performance. It's a nice framework for comparing different approaches.
One thing that stood out to me was their discussion of sequential versus parallel scaling methods. Can you elaborate on that?
Sure. Sequential scaling is where later computations build on earlier ones, like a long reasoning trace. Parallel scaling is where computations run independently, like majority voting across multiple generated solutions. The authors argue that sequential scaling should be better because it allows for deeper reasoning and iterative refinement.
That makes sense. It's like the difference between having a conversation with someone versus just asking a bunch of people the same question and taking the most common answer.
Precisely. And their results seem to support that intuition. They found that simply scaling test time compute on the base model via majority voting couldn't catch up with the performance of their S132B model with budget forcing.
So what are the limitations of this approach? Where do they see future work heading?
Well, they acknowledge that budget forcing eventually flattens out. You can only extend the thinking process so much before the model starts getting repetitive or runs into context window limitations. They suggest exploring things like rotating through different weight prompts or combining budget forcing with reinforcement learning to achieve better extrapolation.
And the context window is a big one, right? The model can only remember so much of its previous reasoning steps.
Exactly. That's why they also experimented with parallel scaling methods like tree search, which can help overcome those limitations. It's all about finding ways to let the model explore more possibilities without getting lost in the weeds.
Overall, this paper is a really valuable contribution. It shows that simple techniques and careful data curation can go a long way in achieving strong reasoning performance and test time scaling in language models. And the fact that it's all open source is a huge bonus for the community.
Agreed. It's a great example of how we can push the boundaries of AI reasoning without necessarily relying on massive resources or closed-source methods.
All right, let's dive into this paper. Cross-attentional autoregressive transformer for multimodal electronic health record embeddings. It's a mouthful, but the core idea is pretty cool, creating better ways to understand and use the massive amounts of data in electronic health records, or EHRs.
Definitely. EHRs are gold mines, but often the data is raw and messy. This paper proposes a new architecture, CAT-EHR, to generate what they call task-agnostic longitudinal embeddings from this raw data. What does that even mean?
Okay, let's break it down. Task agnostic means the embeddings, think of them as compressed, meaningful representations of the data, aren't designed for one specific prediction task, like predicting mortality. Instead, they're general purpose, so you can use them for various things. Longitudinal refers to the fact that EHR data is collected over time, showing a patient's health journey. So these embeddings capture how a patient's health evolves.
Got it. So instead of feeding raw lab results and clinical notes directly into a model, CAT-EHR transforms them into these enriched embeddings that capture both the temporal and multimodal aspects of the data. Multimodal meaning, what exactly in this context?
Exactly. Multimodal refers to the different types of data in EHRs. You've got structured data like lab results, vital signs, and imaging data, and then unstructured data like clinical notes. CAT EHR is designed to handle both and, crucially, to understand the relationships between them.
Okay, so how does COT EHR actually work? I see they mention self-attention and cross-attention mechanisms. That sounds like transformer stuff, right?
Spot on. It's based on the transformer architecture, which has been a game changer in natural language processing. CAT EHR uses self-attention to understand relationships within each modality, like how different lab results relate to each other over time. Then, it uses cross-attention to understand relationships between modalities, like how a doctor's note relates to a patient's lab results at a specific time.
So self-attention is like saying, within this set of lab results, which ones are most important and how do they relate? And cross-attention is like, how do these lab results relate to what the doctor wrote in their notes?
Precisely. And there's also an autoregressive decoder. This is where it gets interesting. The decoder's job is to predict future data points based on the embeddings created by the encoder. This forces the encoder to create embeddings that are temporally consistent and aligned.
So the decoder is essentially saying, if these embeddings are good, I should be able to predict what happens next in the patient's health journey. It's like a built-in quality control mechanism for the embeddings.
Exactly. It's pre-training the model to understand the temporal dynamics of EHR data. Then, once the model is pre-trained, they ditch the decoder and just use the encoder to generate embeddings for downstream tasks.
Okay, that makes sense. So they're using the decoder to help the encoder learn better embeddings, but the decoder itself isn't used for the actual prediction tasks. What datasets did they use to test this out?
They used two benchmark datasets, MIMIC-3 and ADNI. MIMIC-3 is a large dataset of ICU patient records, and ADNI is focused on Alzheimer's disease neuroimaging data. They evaluated CAT EHR on tasks like mortality prediction, ICU length of stay estimation, and Alzheimer's disease progression modeling.
And what were the results? Did COT EHR actually improve performance compared to existing methods?
That's the key. They found that models trained on COT EHR-generated embeddings outperformed models trained on raw EHR data and other baseline approaches. This suggests that CAT EHR is indeed capturing meaningful information from the data.
They also mention ablation studies. What's that about?
Ablation studies are where they systematically remove parts of the model to see how much each part contributes to the overall performance. They removed the cross-attention component and the autoregressive component to see how much each of those contributed. They found that both were important for good performance, especially for AD prediction.
Interesting. So the cross-attention really helps with integrating the different data modalities, and the autoregressive decoder helps with capturing the temporal dynamics. It sounds like they've built a pretty solid architecture for learning from EHR data.
Yeah, it's a promising approach. The fact that it generates task-agnostic embeddings is a big plus because it means you can use the same embeddings for a variety of different prediction tasks. It could really streamline the process of building predictive models for healthcare.
Definitely. And the ability to handle both structured and unstructured data is crucial, given the complexity of EHRs. It'll be interesting to see how this approach evolves, and whether it can be applied to even larger and more diverse datasets.
All right, let's dive into this paper. TIZO, Empowering the Low Rankness on the Temporal Dimension in the Zeroth Order Optimization for Fine-Tuning LLMs. It's a mouthful, but the core idea is pretty cool.
Okay, hit me with the basics. What's zeroth order optimization and why should I care?
So, zeroth order optimization is a way to train models without directly calculating gradients. Think of it like poking around in the dark until you find the best spot. It's super useful when gradients are hard to get, which is often the case with huge language models, LLMs.
Got it. So instead of knowing exactly which way to go, you're just trying different things and seeing what works best. But how does that work in practice?
Exactly. The paper mentions SPSA, simultaneous perturbation stochastic approximation. Basically, you tweak the model's parameters randomly and see if the performance improves. If it does, you nudge the parameters in that direction. It's like a guided random walk.
Okay, I see the poking around analogy, but LLMs are massive. How can you efficiently poke around in such a high-dimensional space?
That's where the low rankness comes in. The authors observed that gradients in LLMs, while huge, often lie within a much smaller subspace. It's like saying that even though you have a million knobs to turn, only a few combinations really matter.
So instead of exploring the entire space, you focus on this smaller, more important subspace. How do they find this subspace?
That's the key innovation of TIZO. Existing methods focus on the low rankness of individual gradients. TIZO takes it a step further by considering the low rankness across all gradients during training, the temporal dimension. They noticed that gradients tend to reside in a similar subspace throughout the training process.
So it's not just about individual gradients being low rank, but also about the gradients being similar to each other over time. How do they capture this temporal low rankness?
They represent the ZO perturbations as a 3D tensor. Think of it as a cube where 2 dimensions are the model parameters and the third is time. Then they use canonical polyadic decomposition CPD to break this cube down into a sum of simpler low-rank 2D matrices.
CPD, that sounds complicated. Can you break that down a bit?
Sure. CPD is a tensor decomposition technique. Imagine you have a complex image. CPD is like finding a few basic patterns that, when combined, approximate the original image. In this case, the image is the 3D tensor of perturbations, and the basic patterns are the low-rank matrices.
Okay, so CPD helps them find the underlying low-rank structure in the 3D tensor of perturbations. What's the benefit of doing this?
Huge memory savings. By capturing the joint low rankness across both the model and temporal dimensions, they significantly reduce the cost of generating those random perturbations. Instead of scaling linearly with the model dimension, the cost now scales with the square root of the dimension plus the number of iterations.
That sounds like a big deal for training massive LLMs. Does this TIZO method work with different optimizers?
Yep, they extend TIZO to momentum-based TIZO-M and adaptive TIZO-Atom variants. Interestingly, TIZO-Atom consumes less memory than even Meso-SGD and only about 35% of the memory of Meso-Atom.
Wow, that's impressive. So it's not just about saving memory, but also about being compatible with popular optimization techniques. What about performance? Does it sacrifice accuracy for efficiency?
That's the best part. It doesn't. The paper shows that TIZO achieves state-of-the-art comparable results with lower overhead in both time and memory. In some cases, TIZO-Atom even outperforms other ZO optimizers.
Okay, so to recap, TIZO leverages the low rankness of gradients in LLMs both individually and across time, using CPD to efficiently estimate perturbations. This leads to significant memory savings and comparable, or even better, performance. Sounds like a win-win.
Exactly. It's a clever way to tackle the memory bottleneck in fine-tuning LLMs, making it more accessible to researchers and practitioners with limited resources. All right, let's dive into this paper. Pivoting Factorization, a compact meta-low-rank representation of sparsity for efficient inference in large language models. It's a mouthful, but the core idea is about making large language models smaller and faster without sacrificing too much performance.
Exactly. We're talking about model compression, which is super important for deploying these massive models on devices with limited resources. The paper focuses on low-rank pruning, which is a technique to reduce the size of weight matrices in the model.
For those not familiar, low-rank pruning is like finding the most important ingredients in a recipe. Instead of using the full original matrix, you approximate it with smaller matrices that capture the essence. Think of it as summarizing a long document. You want to keep the key information while reducing the overall length.
Right. And the paper points out that while low-rank pruning is flexible and works on any GPU, it often doesn't perform as well as semi-structured pruning, especially in terms of perplexity. Perplexity, or PPL, is a measure of how well a language model predicts a sequence of words. Lower perplexity means better performance.
So the authors introduced something called pivoting factorization, or PIFA. It's a lossless meta-low-rank representation. What does that even mean?
Okay. Lossless means they're not losing any information during the compression process. Meta means it works on top of existing low-rank representations. PIFA essentially finds the most important rows in the low-rank matrices. They call them pivot rows, and expresses the other rows as combinations of these pivot rows.
Ah, I see. It's like finding a basis in linear algebra. You have a set of linearly independent vectors, the pivot rows, and you can express any other vector in the space as a linear combination of those basis vectors.
Precisely. By doing this, PIFA eliminates redundancy in the low-rank representation, leading to smaller memory footprint and faster inference. The paper claims a 24.2% memory saving and 24.6% faster inference compared to standard low-rank layers at a certain density.
That's a significant improvement. But the paper also mentions another challenge, error accumulation during reconstruction. Can you break that down?
Sure. When you prune a model, you need to reconstruct the weights to some extent to recover performance. Existing methods often rely on what they call degraded data flow, where errors from previous layers accumulate and propagate through the reconstruction process. It's like making a photocopy of a photocopy. The quality degrades with each copy.
Got it. So how do they address this error accumulation?
They propose an online error accumulation minimization reconstruction method, or EM. It combines dense data flow, the original uncompressed data, and low-rank data flow to minimize the errors carried forward from earlier layers. Plus, it's online, meaning it processes calibration samples sequentially to avoid running out of GPU memory.
So, M helps to reconstruct the weights more accurately by using both the original data and the compressed data as references, and then they combine M and PIFA into an end-to-end framework called MPIFA. It sounds like a superhero team.
Haha, exactly. MPIFA significantly outperforms existing low-rank pruning methods and even rivals semi-structured pruning in performance, while being more GPU-friendly. They tested it on Llama 2 and Llama 3 models and saw a substantial reduction in the perplexity gap.
The paper also compares MPIFA with semi-structured pruning, specifically NM sparsity. What's that about?
NM sparsity means that in every group of M consecutive elements in a weight matrix, N of them must be zeroed out. It's hardware-friendly and can be accelerated on NVIDIA's Ampere GPUs. However, it's less flexible than low-rank pruning because the sparsity pattern is fixed.
And MPIFA can achieve comparable or even better perplexity than semi-structured pruning while offering better GPU efficiency and compatibility. That's a win-win.
Yep. They even have a variant called MFANS, which allows for non-uniform sparsity across different layers and module types. This means they can apply different levels of compression to different parts of the model based on their sensitivity to pruning.
The experiment section is pretty thorough. They compare MPIFA against other low-rank pruning methods like ASVD and SVD LLM, and they also investigate the impact of fine-tuning after pruning. What were the key findings there?
MPIFA consistently outperforms other low-rank pruning methods in terms of perplexity. And when they fine-tune the pruned models, MPFANS achieves the best performance, bringing its perplexity close to the dense baseline. Plus, unlike semi-structured methods, MPIFA enables acceleration in both the forward and backward passes during fine-tuning.
They also looked at inference speed-up and memory reduction. How does PIFA compare to standard low-rank layers and semi-sparse layers in those areas?
PIFA achieves significant savings in both memory and computation time compared to standard low-rank layers. It also demonstrates superior efficiency compared to 2-4 semi-sparse linear layers, achieving higher speed-up and lower memory usage in most configurations. And PIFA's acceleration increases with matrix dimensions, showing its scalability.
It's interesting that they also did an ablation study to evaluate the individual contributions of PIFA and M. What did they find?
The ablation study confirmed that both PIFA and M are crucial for achieving superior low-rank pruning performance. M consistently outperforms full-batch reconstruction and pruning alone, demonstrating its effectiveness in reducing error accumulation. And PIFA further improves performance when combined with M, validating its advantage for additional parameter reduction without losing information.
So, to summarize, this paper introduces a novel framework called M that combines pivoting factorization, PIFA, and online error accumulation, minimization, reconstruction, M, to compress large language models effectively. It achieves comparable or better performance than semi-structured pruning while offering better GPU efficiency and compatibility.
Exactly. It's a promising approach for deploying these massive models on resource-constrained devices and making them more accessible to a wider range of users.
Okay, let's dive into this paper on measuring bias in large language models, or LLMs, from a local context. It's titled LIBRA, which stands for Local Integrated Bias Recognition and Assessment Framework. The authors are looking at how LLMs, despite their advancements, can harbor biases that might not be obvious when you're just looking at a US-centric perspective.
Right? So the big problem they're tackling is that most bias evaluations for LLMs are heavily focused on the US cultural context. This means that stereotypical biases towards other cultures often go unnoticed, and that can lead to unfair or even harmful outcomes when these models are used in different parts of the world.
Exactly. And it's not just about different cultures. The paper also points out that LLMs can struggle with words and concepts that are outside their knowledge boundary, especially when dealing with local languages or dialects. They might generate irrelevant or nonsensical responses, which aren't necessarily indicative of inherent bias, but can still mess up bias testing.
So how does Libra address these limitations? What's their approach to measuring bias in a more localized and accurate way?
Well, Libra uses datasets sourced from local corpora, meaning they're pulling data from region-specific texts rather than relying on crowdsourcing. They created a dataset with over 360,000 test cases specifically for the New Zealand context. Plus, they've developed a new metric called the Enhanced Idealized Cat Score, or ICAT, which builds upon an existing metric but adds in a beyond knowledge boundary score to account for those unfamiliar words.
Okay, let's break that down. What's the original ICAT score, and how does ICAT improve upon it?
The ICAT score, or Idealized Cat Score, is a way to measure bias by looking at how often a model prefers biased sentences versus non-biased ones. It also considers the model's overall language ability. ICAT takes this a step further by incorporating the Beyond Knowledge Boundary Score, or BBS. This BBS essentially penalizes models that don't understand local words, ensuring a more accurate assessment of bias in localized contexts.
So it's like saying, okay, model, you might be showing bias, but are you even understanding the words you're using? That makes sense. How do they actually identify these beyond knowledge boundary words?
They create local vocabulary lists that are different from general English dictionaries. Then, they check if the LLM's interpretation of these local words matches their formal definition. If the model gets it wrong, that test case is marked as invalid, and the BBS is adjusted accordingly.
Interesting. So they're not just relying on the model's output. They're actually checking its understanding of the underlying language. What kind of data did they use to build this New Zealand dataset?
They used over 360,000 articles from local New Zealand media. The dataset includes 167,712 sentences in triplets, designed to assess bias across 8 target social groups. They also paid attention to the presence of te reo maro borrow words in New Zealand English, which can be tricky for LLMs trained primarily on standard English.
And what were some of the key findings when they tested different LLMs using this framework?
Well, they found that models like BERT, GPT-2, and Llama 3 often struggled to understand local words in different contexts. Llama 3, while still exhibiting some bias, generally responded better to different cultural contexts compared to the others. The BERT family models showed stronger text completion abilities, but also exhibited more bias.
So it seems like there's a trade-off between language proficiency and bias. The more linguistically competent models might also be more likely to reflect the biases present in their training data.
That's the suggestion. The paper argues that more linguistically competent models can more accurately represent the biases they've inherited from their training data. This highlights the importance of carefully curating training data and developing methods to mitigate bias during the training process.
This Libra framework sounds like a valuable tool for evaluating and improving LLMs in diverse cultural settings. The ICAT score, in particular, seems like a clever way to account for the challenges posed by local languages and dialects. It's not just about detecting bias, it's about ensuring that models are actually understanding the context in which they're being used.
Exactly. And the authors emphasize that their framework is adaptable and scalable, meaning it can be used to create culture-specific datasets and evaluate LLM biases in different communities around the globe. This is crucial for promoting the development of fairer and more culturally sensitive language technologies. Well, that about wraps it up for this episode. We covered a lot of ground, from clever ways to boost reasoning with targeted datasets and compute nudges, to understanding the complexities of healthcare data with new AI architectures. It's amazing how much can be achieved with focused effort and innovative approaches.
Absolutely. And it's not just about raw power. We saw how crucial efficiency is, whether it's fine-tuning massive models without breaking the bank or compressing them to run on smaller devices. That pivoting factorization technique was particularly fascinating, finding those key ingredients to keep the essential information.
And of course, we can't forget the importance of fairness. That framework for measuring bias in a local context really highlighted how crucial it is to consider different cultures and communities when developing these technologies. It's not enough to just build smart AI. We need to build AI that's responsible and equitable.
It's all about making sure these models understand the nuances of the world they're interacting with. From understanding local dialects to respecting cultural differences, it's clear that context is key. It's exciting to think about how these advancements will shape the future of AI and its impact on our lives.
Definitely. It feels like we're just scratching the surface of what's possible. Thanks for joining us on this deep dive, and we'll catch you next time with more AI by AI.